Okay, first, go through a little bit of how things are going to go down. We've hit the halfway point. You notice that halfway through, pretty much everything you've done so far is just an extension of this is stuff you already knew. Ha! Chapter 3, I would say, is the second easiest in the course. It is just a review of exponential and logarithmic functions and equations. You did it in Algebra 2. Really, it's just whatever you did, turn the dial 1. Like, the equations are going to be a little more gross. That's it. But we know quadratic form. We know we're just better at math now. Okay? So our Chapter 3 is effectively Algebra 2's Chapter 7 if you only use the back half of the assignment. Okay? So it's not tough, not even close. After that, I tell parents and students every year that chapters 1 and 4 are actually the toughest. 1, because it's in-depth analysis of graphs. So you take detail, thinking, graphs, put it all together, and kids don't like that. Especially because that's usually when kids figure out, oh wait, I have to try now, and I've never tried in a math class before. It just happened. Well, now you have to try. So 1 usually does some work. Chapter 3, okay, the quiz dates are all wrong. Like they're off. Just be aware of that. Chapter 3 is going to go fairly quick. I'm hoping we can just rep out a section a day and be done. Like, bam, 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 5 days, there's a chapter. Okay? In which case you would have your next quiz on Friday next week. Okay? After that, we go into chapter 4. That one is, it's your introduction into trig functions, which is something you should have done in geometry. I know you didn't. Or at least the right triangle trig, the unit circle, radians, all that kind of stuff. You should have done geometry. I know you didn't. The trig functions, well, we didn't do it in Algebra 2 because they're not doing the other stuff in geometry. So it just keeps getting pushed back and back and back and back. Here it is, which means we're going to end up spending probably 3 weeks in that unit. It's a big one. Okay? But after that, it's kind of just a slide down to the end, like all of November, chapter 4. After that, it's kind of a slide to the finish. 6 is super short. We do matrices and partial fractions, just basic stuff that you need before you go up to calc.
Wait, do you do 7 before 6?
I do 7 before 6 because 7, last year, I didn't know how far we were going to get. Last year, first semester, I had a very good crew, but they were slow. Like, they did amazing, but they were just slow. So we ended up having to cut out stuff. Also, that's when last year my pre-calc was split into cohorts. It was maroon or white days of 12 kids, just to keep spacing in here. So, yeah, I was the only one in the district because South Dakota that actually gave a rip and fought for it. Because I would have died. We had chapter 7 before 6 because 7 is absolutely mandatory moving up to calculus. You have to know that. Technically, it should have been an Algebra 2 thing. So we make sure we get 7. We had to cut some stuff out of 6. I'm okay with switching up the order like that because those two chapters got nothing to do with each other. And then 10, you come back after our holiday break there, and chapter 10 is actually the easiest of the entire course. We end with you know this formula? Yeah, throw numbers in it. Ta-da! Like, it's super, super easy, but it's also one of those things that just shows up on ACTs, and it can be the thing that gets you. Sequences, series. Sigma notation, it's not tough. So you're at the halfway point, but so far half of it has been just pounding on the things you know and extending them. After logs, it's gonna be all new stuff. Okay? Not tough stuff, just new. Particularly when we hit chapter 4. If you're kind of on the border, y'all know that you need a C in here to move on to trig. If you're kind of on the border, like say you get out of this class with a 78, okay, an 80, you know, you got your C, you can move on. But we look at your chapter 4. We look at how that went. Because if you got out of here with a 78, but your chapter 4 stuff was all like bomb after bomb, we're going to tell you, you know what, you can go on to trig, but you probably shouldn't. Because it's literally the stuff you need to know going into trig. It'd be like if you came in here not knowing how to do a quadratic. Okay? So it's new, it's important, it's not difficult. But because it is brand new, you're going to have to lock it in and not be screwing around the whole class or disappearing for 15, 20 minutes at a time in the middle of class. Or. All right? You're going to want to kind of lock it in for that. So, your quizzes, no idea when I'll get them in. Other than they have to be in by Wednesday morning. Daily work, just got through all the junk. Other than a couple of scattered missing assignments, most of it is good. Anna, I didn't get your stuff. So. Okay. Yeah, I'm just. Oh no, don't do it today. I'm never going to get to it. It's a white day. White day sucks. So, if you just get that to me like after class tomorrow, and then I can do it during my prep. I just want to make sure I get it in. So, that's what we're doing. We start with the trip down memory lane. You did exponential functions all the way back in Algebra 1. Exponential function is anything that is of the form a times b to the x. Do we remember what everything's called here? Those three all have a special name. What are they? X is the exponent. A is a coefficient. Okay, in the context of exponential functions, it'll often be called a growth or decay constant because it's what you multiply your exponential growth or decay by. B, all about that base, Yep. Okay. When I smack an entire exponent together, if I say like 7 to the third, quick, what's 7 to the third without a calculator? Boo. 343. Okay. Okay. This would be considered the third power of 7. So when you smack the base and the exponent together, you call it a power. Okay? So it's a little bit, it's one of those things where I'm never going to throw vocabulary on a quiz, but you got to know it or else you don't know what they're asking you to do. So, exponential functions. They give you examples and what's not an example. Just because it has an exponent in it doesn't mean that it's an exponential function. It has to have the variable up in the numerator. We know how to do exponent stuff. Yay. All right, before I go doing that, I have to just because. Please tell me you remember your exponent rules. B times C. I was listening to those putzes flap their lips. So, you know what?
Wait, we have to erase all the other ones.
So is Andrew responsible for the whole back table?
I'll let Anna and Taylor decide that. Is he responsible for the entire back table? In terms of if anything goes wrong in that corner of the room, it's his fault.
Yes.
Okay. So, okay. The reason that we can do that is because if I ever have 1 over a to the c, do you remember how I can bring that upstairs? Or more appropriately, you're probably used to a to the negative c is what? 1 over a to the c. A negative exponent just flips the switch, numerator or denominator. It's the reciprocal feature. So the reason that this is b minus c is because I can bring that up top as a to the negative c, and now I will just add those two together. So that's why it works. If I have a to the b, c to the d, all to the f, they all get that exponent, right? So you got to be careful when you're dealing with exponents as to what the exponent actually applies to. That's why we use parentheses. That's why all the way down to algebra half, I hammer on them to use parentheses because they're going to keep us from screwing up exponents and negatives. And then everyone's favorite, uno. And that works for anything. If I took that, 1, in fact, those rules are still over there from week 1 of Algebra 1. Okay, so we got to make sure we remember how exponents work before we start graphing them and using all those function business. Do you remember how to get all of your perfect squares, cubes, fourths, and so on your calculator? Nice and easy if you don't know them off the top of your head. Instead of just guessing, checking, and poking buttons. Why is? I'm going to say y2 is x squared. I'm going to say y3 is x to the third. I'm going to say y4 is x to the fourth. y5 is x to the fifth. Why did I skip 1? Because anything to the first is itself. So now if I go to a auto-populated table, going by ones, there we go. Ba-dum-bum. Now I have all of my squares, cubes, fourths, and so on. You should know, y'all are in PreCalc, you should know through 20 your squares, through 10 your cubes, through 5 your fourths, and then as many powers of 2 and 3 as you can possibly memorize. You should just know those. All right, the same way that coming into algebra when you're probably in middle school, if you didn't know your multiplication facts, you were just screwed. Think about when we first did factoring quadratics. What is it? What factors of a negative 51 add up to 14? You should know off the top of your head what everything in that 20 by 20 multiplication chart is. And if you didn't, wasn't factoring kind of a guess and check game? Or you had to look at a multiplication chart? Or you had to list out all of your factors? If you know it, it makes life easier. If you don't, you can still do it, it just takes more work. Same thing's going to go with all of our exponents. If you know them off the top of your head, it makes life easier. If you don't, you're going to have to do more work. Okay? Two to the seventh. There you go. All right. So if we're going to sketch and analyze, look at what it's starting with. What we started every section with in Chapter 2. Chapter 1, we learned how to analyze the graphs, and then after that, every time we run into a new type of function, they say, hey, tell me all this stuff about it. So, if I'm going to say all this stuff about it, I should probably write things first, like graph. It's 3 to the x. Well, what is 3 to the 0? 3 in the first. 3 in the second. 3 in the third. 3 in the fourth. Do it in pieces. 3 to the fourth. 3 by 3 is 9. 3 by 3 is 9. 9 by 9 is 81. Do it in pieces. Okay? What is 3 to the negative first? 1/3. Don't go to decimal town. 3 to the negative second. 1/9. So you use those fractions. 1/3, 1/9, 1/27, 1/81. And if I keep chopping that thing into thirds, when will it be nothing? Never. Okay? If we were to take Grace and chuck her up in the air and just fruit ninja her, when will there be no more Grace? Never. The pieces will be very small. We will have Grace soup, but there's still Grace, right? You're never actually going to get to 0. It's the classic problem that you get back in like middle school is, what if a store had a half-off coupon, but they forgot to put the limit in the fine print at the bottom? Could I just come up to the desk and be like, Half off. Half off. Half off. And just keep doing that and make them keep hitting the button. Will it ever actually be fully free? It'll be close. You could basically hand them belly lint and they'll just say, go away. But it's never free. What is that called? What feature is that if it will never hit 0? We just did a bunch of them. Asymptotes.
No, that's like one of the laws or something. You know what I'm saying? I don't know.
That you can't actually hit absolute 0. Yeah. So what I had always called these in Algebra 1, Algebra 2, we called them the creeper functions. It creeps along, it's hanging out in the bushes outside your living room. It's creeping along, creeping along, creeping along. Oh God, they see me, and they take off. Creeper functions. Sam Tobin. Okay. So they just creep along the asymptote and then shoop, they take off. What you're going to find with these is even if I put a...
The law of conservation of mass.
Okay.
Paul.
Paul's over there just saying random science stuff, hoping to sound smart. Okay.
Can't destroy Oh, Paul.
Okay. We have, if I take this graph and I multiply it by a coefficient, what type of transformation is that? Vertical stretch. Or we'd call them just dilations. Vertical dilation is it's going to stretch or compress. What you find with exponential functions is because an exponent is so much more powerful than a coefficient because it's repeated multiplication instead of a multiplication, is that it might change how the graph looks right here a little more dramatically, but after you go just a little bit to the right, it don't matter. It's still gigantic. If I put a 1/2 in front of this, well, half of 1, half of 3, half of 9, but then half of 27, half of 81, half of 243, half of 729. It's just going to keep getting bigger and bigger and bigger to the point that that coefficient almost doesn't matter. So we just have to know that. Yes, there will be transformations, but they're not going to affect it nearly as much. Okay, once I got that graph, can you tell me all the stuff about it? And you know what? I'm going to assume that you can write all the things, but let's just run through it verbally to save ourselves a little bit of time. Domain. What is the domain of that function? All real numbers. 2 reasons. A, I literally see the graph go all the way to the left and all the way to the right. 2, is there anything in there that violates the commandments of domain? An x on a denominator, a even radical, a logarithm, an inverse trig function. I don't see any of it. So, domain's all real numbers. Range. 0 to infinity with a parenthesis. Continuity. Remember, you state along what x's it is continuous or not. Can I put my pencil at negative infinity and continuously trace it without ever picking my pencil up?
Yes.
Yeah. So it is continuous for all real numbers. Symmetry? Nah. X-intercept? X-intercept? None. Y-intercept? 1. What else? Oh, intervals that increase and decrease. Where is it increasing?
It's always
Yes.
Negative to positive infinity. Yes, it is always increasing. It is never decreasing. All that stuff. Oh, and behavior. Limit as I approach negative infinity. Good. Positive infinity. Okay. So we know how to do this. It's just a matter of, do we remember what the graph looks like? So, I would like you to graphify those two. And you don't have to write all this stuff, but I would like you to at least talk with some of your neighbors about, do you know what all of this stuff is? Can you analyze the function still? Remember, if you get completely stuck, you can always graph by table. Oh, I know. That's why I got them. It's just got a bunch of beads in it. It's squishy.
Oh,
Squishy.
you ever seen those boxes where you, like, when you slide them open, like the rack comes out?
Yeah.
Like, big
Yeah,
rack.
it
Oh.
comes up with it.
Yeah. I don't know why it was that little rack when you get that. Which one for the main power? I feel like it's just 4. I'm not sure how I'm supposed to do it. Let's see.
Uh-huh.
Like these 4. I feel like this is
If you can look at it and you can tell me the stuff right now to save us time, no. Like in our assignment, I might include one of these.
No, because you have to have one. Because this is the one. That's not. No.
wait, the aspect is
Okay, that's where they should be. See a good number of you graphing by table. That's okay. I want to show you, you don't have to. If you just know your powers, 2 to the negative x, what does a negative exponent do? Flips. So that means, if I went really old school here, womp, right? Anything to the 0 power, even if it's on denominator, is still 1. But if I plug in 1, that's 2 to the negative first. 1/2, 1/4, 1/8. So that means when I put in -1, a negative negative is positive. So as long as you know your powers of 2, it's just the reciprocal of it. Which should make sense because y is a times b to the, we have to use something else now, c x minus h plus k. Member transformations. Now I have to call it a c because b is my base, but what does that c spot do in transformations? That's grouped with the x. Horizontal, stretch, compression, and reflection. So you take your powers of 2 and you just reflect them. Instead of going that way, I'll go this way. So 2 to the first, 2 to the second, 2 to the third, 2 to the negative first. Well, now it's on this side. So 1/2, 1/4, 1/8. If you know your powers of 2, you don't have to use the table. So if this could be rewritten as 1/2 to the x, right? 2 on denominator. Could you use that and extrapolate to find 1c? Treat this as that, right? And just flip it, which means it'll be a horizontal reflection of the original 4 to the x. I'm also going to have a vertical translation where we're going to head up 1. So that asymptote that was at 0 is now up 1. I just do my powers from that asymptote. 1, 4, 16, 1/4, 1/16, and so on. Oops. Okay. Yeah, aim like that is how you accidentally nail a kid in the eye with a Nerf gun. Because Lars moves. It kind of ricocheted off the board and hit the kid who was writing over at the board. Like, right in the, yeah. Oops. But once you have the graph, you're okay analyzing it because they all follow this behavior. No, we're not doing the other two. No way. Okay. Like, you know how to graph by table. You can then analyze a graph. We've done it for months now. Okay. So, could you name the transformations? Maybe that's something that we need to write. So maybe down here you got some room. We have y equals b to the x. Every time I change b, every time I change the base, it's a new parent function. So you have to understand that y equals 2 to the x versus y equals negative 2 to the x, those are actually different families. Every time you change the base, it's a new function family. Now, could I write something like this maybe in a different form? Yeah. But you got to be careful about it. Every time you have a new base, new function family. The transformations are A. I hope I don't have to write them anymore. Beat them to death in Algebra 2. We didn't again in here. What does A do? The number that's in front of. Vertical stretch, vertical compression, vertical reflection. Another name for vertical reflection. Reflection in the x-axis. Okay. What about horizontal translation, or big kid words? It's going to shift right and left. And remember, because it's grouped in with the x, it's bass-ackwards land. Okay. If they say to the x minus 5, I'm going right 5. Because every input that I have, I'm going to take 5 away from it. So it's going to take 5 units longer to get where I'm going. All right. How's about, okay, vertical translation. And that's regular because it's not grouped in bass-ackwards land. I'm taking my output and I'm moving it up or down. And then it's not really stated, but if I have a C, that's going to be a horizontal stretch or compression, horizontal reflection, and it's grouped with X, so it's bass-ackwards land. You got to remember that if C is a 1/3, that means I'm taking my input and multiplying it by 1/3. Think about a timeline. You're trying to save up for a new car. And then if I take your income and cut it in 1/3, what does that do to the time it takes to get your car? Triples it, right? So it has the opposite effect. If I see a C of 1/3 instead of being a compression, that's now a horizontal stretch by 3. It's going to be a reciprocal effect, bass-ackwards land. Okay. Speaking of, I don't know, y'all teenagers, anyone shopping for cars? Maybe. You seen the prices? Mother of God. Well, not even used cars are just bonkers right now. My truck is now 5 years old, and it's worth $8,900 more than what I paid for it. But then what would I drive? I would have to, yes, but what happens when I drive and then she's at home with child and child, I don't know, has to go somewhere? Yeah, I probably shouldn't do that since I'm driving the other child. Ew. You seen that thing? It's like a lawnmower. All right. But anyway, I was talking with my grandpa the other night about prices. He's wants to get a new truck, but he's a cheapskate, so he won't do it. I'm like, you're sitting on money. What's going to happen? You're going to die, and your kids are going to fight over your money. Just spend it and have fun. But, nah. Anyway. Y'all remember this dude? E. I'm not going to bother with these because you know how to move things up, down, right, left, reflect, stretch, and even if you don't, can't you just graph that by table? What two transformations happen to it? Vertical reflection or reflection in x-axis, bass-ackwards land, horizontal translation, 2 to the left. Yes, sir.
Okay.
So are there any of them that are weirding you out?
Yeah. So I was kind of confused because if you plug in a negative number for like the coefficient and then put it to like x, like I plugged that into my calculator to see what would happen, and it doesn't work really. I'm kind of confused.
Are you using parentheses?
Yes.
Are you using the right negative?
Like if you go -2 to the x, right?
Uh-huh.
And then you go graph.
Oh, no. That's if you're saying the base itself is a non-positive number, that's definitely going to change things. If you try to say -2 to the x, I want you to think about that. What's -2 to the first? What's -2 to the second? +4. -2 to the third? -8.
So how does that get worse?
What happens when I use a non-integer number? When I use -2 to the 17/5?
I was wondering that the whole time.
It creates this split. But within there, depending odd or even, depending rational or not, there's a infinite number of holes. There's an infinite number of holes because in between, because it's going to have an even power, odd power, backwards. Even power, odd power, even power, odd power, even power, odd power. Well, in between them, you're going to have rationals that are both even and odd. And there's going to be an infinite number of holes in between there, but there's also an infinite number of points depending on what denominator you used, and it creates chaos.
So when you have a negative,
Come back in Calc 3. Yeah.
so when you have a -2, so like say you have a negative number like that,
Uh-huh.
so I have two exponential functions, or like rather than making a big squiggle.
Right, it's not going to go back and forth between them. Chapter 4.
Oh, I was gonna say this has
Literally, sine wave. 0, pi over 2, pi, 3 pi over 2, 1, -1.
Yeah.
Literally, chapter 4. We're getting there.
I think I need to drop out.
The reason that people freak out in chapter 4 is because A, you haven't worked in terms of pi before, because you didn't get it in geometry, because and B, you have to graph, and kids just love graphing. C, everything needs to be written in terms of pi, so you have to write it all in fractions. Fractions involving pi. So you combine fractions and pi, which is new, and graphing. That's why kids hate chapter 4. Because you combine the three things that kids hate the most.
So is that the chapter that both girls cried? Like we were talking about volleyball girls, how they would just sit.
No, that was chapter 1.
Oh, wow.
So, anyway, so ignoring negative bases, that is a valid question. We're going to define our function. You know what? I think, coming all the way back here, Andrew, read that very first sentence.
And
An exponential function.
An exponential function with base b has a form f of x equals a b dx, where x is any real number and a and b are real numbers, constants, such that a does not equal 0, b is positive, and b does not equal 1.
B is positive.
Okay.
Specifically a part of the definition for that reason. It's a good question to have, but it's part of our definition because of that. If b equaled 1, what happens when you take 1 times 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 1? Yes, it's the constant function. It's just a horizontal line at a. Now, if b, my base, happens to be this special feller, we learned about e in Algebra 2.
Isn't that how you get like natural log and stuff? Yeah.
Can't you put stuff above that?
No. So here, okay, here's what, let's say tonight I assign you 100 problems. And then okay, let's say I assign you 20 problems. You know what, let's make it better. Let's make it actually divisible by 2. Let's say I assign you 16 problems. But then tomorrow, I am going to add half of what I added the previous day. So we start at, you're going to do 16. I'm going to add half of that, 24. How much did I add? Okay. I'm going to add half of that amount the next day. So now I'm going to add 4. So 24 plus another 4. 28. I added 4 the previous day. Now I'm going to add 2. 28 plus 2. Now you're at 30. I'm going to add half of that. Half of 2 is 1. I'm going to do 31. And then. Now I'm adding half a problem. Now I'm adding a quarter of a problem. Now I'm adding an eighth of a problem. Now I'm eventually it's just like put a dot on the paper. Eventually I'm adding nothing, right? Almost nothing. That's what this function is. 1 plus a portion of itself that many times. It's called continuous growth. When something continues based on itself, eventually you're not going to add anything. This graph looks like this. And its limit, that asymptote where it eventually is adding nothing, is at E. We got that last year. Okay, E is its own special base. In fact, it's so special that it got its own irrational number form, just like pi. It has its own button on the calculator. Everyone know where it is? There's E and there's E to the x. You're definitely going to want to know where E to the x is. Okay, you want second function E, not alpha E. Okay, here's E to the x. Yes. So what I'm saying is like not alpha E. You don't want this E. You want that E. And then E to the x. Okay? So if you just want to use E itself, there. That way you don't have to do E to the first. Right? E to the x, you would have to do E to the first. If I just want E, then just press this button. Okay? But not alpha, big E. This is also why throughout algebra, we never had E as a variable. You go all the way back, like dig through Algebra 1 textbooks, go back to geometry. You never had E, lowercase e, as a variable. Because it means something. It's important. It's so important that when I was in college, I attended a debate between 2 math professors about what is more important, pi versus E. Like, it was a traveling symposium between two math doctorates. And it was like an episode of Big Bang Theory where they ended up hurling scientific yo mama jokes at each other, and they got mad and like had a hissy fit. One of them stomped off stage. It was great. Pi versus E. The reason that E happens so often is because it's the natural base. It's when natural things grow based on their own population. Y'all been through biology? You do the swab thing where you get the little colonies and you find out how gross your phones and the doorknobs are? Oh, okay. Well, oh, well, okay. It's a thing. But think about, grasshoppers. Think about your grasshopper population the last 2 summers. Okay? It was bonkers. Like, I'd walk out in my yard and there would be this cloud that just kind of floated in front of me, and they land on you and the little pincers get you and it feels like they're electrocuting you, and yeah. So, but there's a natural limit to it. If they're growing based on their own population, they will explode exponentially. But what happens when their food supply goes away because there's a frigging drought? They'll kind of level off.
I feel like they come more.
Yes, because there's not enough of the other bugs to keep them in check by eating them. But they do still hit that limit because now there's not enough vegetation. We talked about it in biology called homeostasis. Right? It's a natural systems balance. Something can only grow based on itself for so long. So there's a limit to it. That's why E is so important. That's why if you go on into chemistry, how many juniors playing around with chemistry stuff? Okay. First semester is mostly terminology, a lot of vocabulary, building molecule models, that kind of stuff. Semester 2, you go to equation town. And you will start seeing E an awful lot because things happen naturally with growth and decay in terms of chemical compounds. So you're going to start seeing that E an awful lot. For our purposes, it's just another base. When I hear the word continuous or natural, I know that E is involved. I can still tell you all of the transformations that happen to it, right? Like, without even knowing what E is, what 2 transformations happen to the parent graph? Horizontal reflection. Vertical translation up 3. There we go. Feel like I'm up here like, ah! Okay. So, if most people aren't going to know what their powers of E are, I remember about 2.72. I remember, or 7.3. And then about 7.29. Just because 729 is a 9 to the 4th and all that. So it's familiar. Not 9 to the 4th, 9 to the 3rd. I'm tired now. So if you don't know the powers of E off the top of your head, to say it's a horizontal translation, or sorry, vertical translation up 3, powers of E, and they're all reflected horizontally. Well, anything to the 0 is still 1. Anything to the first is itself. E is about 2.7 blah, 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 blah. E to the second is about 7 point blah, 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 blah. Well, isn't it still going to do the same thing that every other exponential function does? Right? It's still going to creep along the asymptote. It's still going to take off sharply. It's just the actual number values are all going to be in terms of E. So they're going to be gross. So I'm probably just going to graph all these by table anyway. because if you don't know your powers of E off the top of your head, you're probably not going to be able to graph it without using the calculator. So that's all I want you to do. Make sure that you can graph by table and tell me the transformations. Let's get funky. Go! Well, I hear that and I think there's an old commercial for Punkin' Chunkin'. Like Punkin' Chunkin'. It was a Thanksgiving special where they do like pumpkin air cannons and trebuchet division and catapult division, human propelled division. Like, they're super cool.
I definitely don't think of that. I think of that song that everyone dances to. I don't know what it's called though.
The song in the commercial was "I like 'em big, I like 'em chunky,
That just makes me think of that
I
song.
like 'em loud, I like 'em funky." It was something. If you've never made a trebuchet, I highly recommend it. Incredibly dangerous. I still have a dent on the left side of my head from one. So. That isn't this graph. That's the parent graph. And then we're going to do stuff to it. Because most of you are probably right now just graphing by table. I want to show you the transformations as well. Okay. Original parent graph. E to the x. E to the first, 2.7 blah, 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 blah. E to the second, 7 point blah, 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 blah. And then the reciprocals of those are going to be tiny fractions. Actually, not in fractions because it's an irrational number, but you get it. Then, first thing I'm going to do, I'm going to move my asymptote down 4. All right, 1, 2, 3, 4. When I do, all that stuff would kind of come with it, right? There we go. So this point that is normally just 1 above the asymptote is going to be 3 times as far above the asymptote, and we're going to move right 2. So 3 times as far above the asymptote and right 2. Then I use my values of e to the stuff. Well, e to the first is normally 2.72 whatever, whatever, whatever. Take it times 3. So now we're going to be up at 8 point, what, 1, 2, 3, 4, 7, 8 and change. If I have e to the third, Well, that's just going to be gigantic, right? Because now it's going to get multiplied by 3 as well. So it's going to be like 21 something then times 3. It's going to get big. Way off the graph. I'm going to have e to the negative first. Well, is normally 1 over e. Well, now it's 3 times as big. So it's just going to be whoop. It takes those same features and it just stretches them out. As long as I see a few points on there that says I looked at my calculator and I plotted a point, you're good. Okay? Gaze into the crystal ball, right? All right. So graphing, same old, hi.
Oh yeah, -7. And like -8 and -9.
Highlight them.
Oh.
All right, that.
It just gets so small.
Yep.
It just can't. Oh yeah.
No, in the calculator, when you're graphing by table, the cell where the y's go is only so big. And after a certain point, they're just going to give up. But if you highlight the cell itself, you will see the number. And then it'll eventually switch to scientific notation. And then if you keep going far enough, the calculator will just give up and just say -4. Okay, so there's some stuff. Y'all remember, probably back in middle school, maybe Algebra 1, the whole interest problem stuff. Okay? The first times you did it, you had to do it manually. It was something like, you're going to put $500 in the bank account, and you're going to get 2% interest on it. Every year. And you're not going to touch it, and you're going to leave it in there for 10 years. How much is it worth at the end? Well, what's 2% of 500? $10. Okay, follow me on this magical path. What's 1% of 500? 5 times 2. 10. Okay, so I'm going to add $10. But now I have $510. What is 2% of that? $10.20. So the next year I have, and then 10% of that, and then 10% of that, and then 10% of that. Every single time, 2%, yeah. Maybe we switched over to the Mafia Bank, I don't know. So eventually, you're going to get there, but it takes forever. What someone comes along and does, famous dead math dude, is they turn it into a formula with a sequence. They say, every turn, every year, I'm going to take what was there before, plus the thing times my rate. Well, if I factor out, I get this 1 plus r thing. Well, it turns out I'm just using that 1 plus r thing every single time. If I'm always multiplying by something repeatedly, I can express it as an exponent. And if I do, eventually it turns into a formula. Formulas are nice and easy. The amount is the principal 1 plus the rate over the number of times it's compounded. This is, again, number of times compounded. And t will be time. most often in years. Like, if you start to get even remotely interested in finance, you'll find that quarters are a big deal. You ever listen to NPR? They'll talk about the quarterly report. Every quarter, the Federal Reserve updates their rates, that kind of stuff. It's very, very few kids that give a rip about that, but it kind of runs your life, and you don't know it. The number of times something is compounded is how many times do I figure out my interest every year. So we got to know a bunch of those words. If I say that something is compounded weekly, 52 weeks in a year. Well, technically 52 and a seventh, or 52 and a quarter. But, okay, 52. If I say that something is compounded quarterly, well, most people know that's 4. But what if I say no?
Biannually, every 2 years.
Biannually is every 2 years. So if it's every 2 years, how many times are you doing it in a year? A half. Semi-annually, I do it every half of a year, so twice a year. And what's really annoying is that there are financial institutions that will use biennially, not biannually, biennially, to mean semi-annually, just with an E instead. It's really annoying. English language, go us. Okay, so you have to know just stuff like that. Do you know how to calculate, when is it a leap year? Every 4 years. Is this a leap year or not? How do you know that?
Because I just know random things.
Y'all, what's 100 divided by 4? So every 100 years is another leap year because 100 is divisible by 4. So that means just take the last 2 digits of any year, and if that is divisible by 4, it's a leap year. So last year, 2020, is divisible by 4. That was a leap year. Why we needed an extra day that year? 2021, well, 21 is not divisible by 4, so it is not a leap year. Okay, it's every 4th year. So technically there's 365.25 days. Like, there's an actual mathematical proof for it. But we're just going to say on leap years, 366, not leap years, 365. Like, you just got to know some of this random stuff that goes along with basic context. So,
Like July 31st, and then July 30th, and that one day is February, and then like August.
why would we do that? It would almost make sense. Have you heard of daylight savings? Yeah. We should. We really should. Every year there's an increased push for it.
Isn't it Arizona that they don't have time frame?
Correct. I lived there for 3 years, and during the winter, I was 2 years behind family when I called them. 2 years, 2 hours. Right? All right. Blah, 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 you got a formula. Okay? Formula. Yeah. We got 2 Annas in the room, so we're just going to go with the 3rd Anna. Okay? Because I don't respect anyone with the name Christy. So, I've just never met one that I liked. Anna is going to invest $300 in an account. 6% interest rate. Y'all, 6% interest does not happen. 6% interest is a shady mafia bank.
Or interest on loans.
Banks will not give you 6% interest. 0.06 is actually like a good rate these days. If when I was in high school, I could have my money in a bank account and I could have maybe 2% interest. Okay? That was 20 years ago. Now it's more like 0.02% interest. And when I get my annual tax statement that says technically you earned money, so you have to turn this in, I hand it to our tax professional because I don't want to be liable. So even though I can do the taxes, I don't care. They're going to do it for me. I hand the piece of paper to him and he says, I don't need that because I earned like 31 cents. Okay? So just know that this is not remotely accurate. This is Mafia Bank. You will never make this in your lifetime. Well, rich people kind of have a tendency to subvert the law anyway or use financial institutions in their favor, so they're doing that crap anyway. Mafia. Semi-annually. I'm going to say we got $300. 1 plus. If it's rate. 0.06. Please tell me that you remember decimal to percent or percent to decimal is always 2 places.
That's the only thing I remember.
Okay. So I'm going to say 0.06 over. If it's semi-annually, how many times is it compounded every year? And we're going to keep going and we're going to find something interesting. 2 is how many times we're doing this, and it's going to happen for how many years? 20. So jam that in your calculator.
Wait, is it 1 minus or 1 plus?
1 plus.
When do you use the minus?
Minus is when it's a decay. This is interest they are paying you, not interest that you, or value that you are depreciating. Okay, so 300. 1 plus alpha y equals thing. 0.06 over 2 is to the 2 times 20. Womp. Okay. So after 20 years, you got this.
Isn't it? It's the rate though. It's R times T. Because the exponent when we.
Was it R times T or N times T? It was N. Okay.
What was the rate of CDs? Because I know that was the
He tripled the amount of money.
Depends on the length of it.
10 grand.
3 to 5 year CDs, maybe 5%. If you go to like 20 years, then they might go up to like 10%. But there's penalties when you withdraw it early. Okay. Yo, back over here. The same thing, but we're going to compound it monthly. Right? Because it was A, B, and C. I just highlight it. Now, normally, if I were to try to hit 12 right here, it's going to overwrite it. Second, insert.
That's how you do that?
Yeah. It's the same as a keyboard. You have the insert feature. I mean, it's automatically in insert mode nowadays. And then,
Oh my god.
okay.
Oh, that's not it.
So I went from twice a year to 12 times a year, and it jumped up, what, 15? Okay. What happens when I do the same thing, but now it's daily? What changes? 3 6, 5, wait. No, they're just figuring out your interest every day.
You only went up $2.
You only went up $2. So what would happen if I said then do this hourly?
Oh, I
Change to
no.
65.
And then go up like $1.
What if I did that same thing, but insert, and I'm just going to throw in another times 24, just because I don't even want to figure it out. 365 times 24. Doesn't change that much. What happens if I did this every minute?
Oh.
And then every second?
Let's just not figure it out.
Eventually, I'm practically adding nothing. It's almost like there's a limit to it. E. Yes. You've all heard it scientifically, the law of diminishing returns. The more you do a thing doesn't mean that you're going to get more benefit. Sometimes that's just as good as it gets. That's what's going to happen with these. I hope you wrote down those amounts, by the way. Don't worry about down here. Okay? And it turns out those answers were right there. Yeah. So when I plug that in, I see that as I continue semi-annually, quarterly, monthly, daily, hourly, eventually I'm adding next to nothing. I'm adding continuously in terms of my time. So if I keep adding continuously, I might as well rearrange my formula with that limit function in there and up. New formula. Bert. Hey, Bert. P is still principal, rate is still the rate, T is still time. The only difference is y'all, I want you to write something very, 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 very important here. You use E if you hear the word, if you read the words continuously. If it says continuously, you're going to use E. If you do not see the word continuously, then you have to assume that it is done either annually or whatever word they said. But if I ever see continuously, that's when I use E, not any other time. And then I'm sure you can press buttons. Okay. Oh yeah, that's right. This lesson does like 3 1 3 1 3 2 3 2. All right.
Wow, the homework's great tonight.
It's just graphing and like 2 formula things.